Hi, I wanted to make a video today to show you a workflow that I am working on in structural engineering design practice that I've been using AI systems on. I thought the workflow would suit AI systems well, and I will be honest, some of the models really exceeded my expectations for how they would perform, and I wanted to share that with you. So this is going to be a longer form video. If you want the TLDR for how the models performed and what the end conclusion was, you can see that on my LinkedIn and my Substack. I'll post those in the comments or the bio, whatever the hell it's called. Um, I'm not really great at making these types of videos, and I don't have all the time in the world to edit them. So this is going to be really raw, and I apologize if I kind of like stumble my way through this, but this is what I wanted to show you and what I've been building. And like I said, I'm really, really impressed. There were some parts of this workflow where these systems were doing things that me as an engineer and other engineers that I work with wouldn't do it that way, but it was really intuitive and I thought it was really interesting. So I wanted to share that with you. All of that being said, what this workflow entails is I'm acting as an engineer, a delegated design engineer for the engineer of record. We're working on a steel frame structure. And my role in this job is to look at the existing structural system, take the new loads that we're getting from the engineer of record, and assess the capacity of the lateral force resisting system and figure out whether we need to reinforce different types of connections or not. So typically, how would this workflow work and how was I doing it before I decided to use AI in this workflow? Well, we were given the existing shop drawings, and we then went ahead and we created an Excel spreadsheet. And in the Excel spreadsheet, we're modeling all the different failure mechanisms to expect in a lateral force resisting system. And in the Excel spreadsheet, we're given the different elevations, the different locations of where the connections occur, and then we're pulling in the new loads that we're getting from the engineer of record. And what I had to do was go through the shop drawings and populate 13 different columns per each connection. So we needed to look at the different types of members that were getting framed to the connection, whether it's a weak axis or strong axis connection, different connection types, the bolts being used, whether there were doubler plates being used on the columns in the instance of a weak connection, and then going through both the shear and the moment connection. These were all different variables that we were trying to identify and then populate a spreadsheet with to figure out what the utilization ratio was of that connection. And then once we understood that, we make the decision whether we had to reinforce the connection or we were happy with the state that it was in. So how I would go about this workflow is I would get the elevation, I would get the phase, and the phase is the building's broken up into three different phases in this instance, A, B, and C. So that determines what drawing I'm looking in. And then I would go to the specific grid location that we're trying to investigate. And I would look for all these different variables by reading through the shop drawings. And this is a simple example. This is the mezzanine level. This isn't even like the full bay or all the full structures, but I thought this was a good sample size to really run this experiment against. So what we're looking at right now is just the on-plan framing section. And typically what we would do is we would go through each connection and we would find the different piece mark drawings. So you get a column piece mark or a beam piece mark, and you'd slowly work your way and read your way through the drawings to get all of the variables that you needed before. This is a very tedious process. At first, it was taking me about 10 minutes per connection to really read through everything thoroughly and get the proper information out and populate the spreadsheet with it. As I got more familiar and comfortable with the drawing set, I got it down to about 3 minutes per connection, which wasn't terrible. But I wanted to see if there was a way for these AI systems to extract this information at a higher accuracy level or maybe faster than what I could have done as a human engineer. And that's really the basis of the experiment that we're going to go through here today. So looking at this little Claude presentation that Anthropic put together for me, what we did was we have these 13 fields. I did the initial takeoff myself. So there were 21 different connections in this sample size that we were looking at. There were 13 variables that we were trying to identify per the 21 connections. So there were 273 different cells that needed to be populated. And then I used one participant as myself and then 4 different AI models. I decided to use the Opus 5 model, the Fable 5 model, Grok 4.6, and the ChatGPT 5.6 Sol. So these are the most high-end models at this moment in time available to the general public. I'm shooting this video August the 12th, 2026. So using these different models, I was able to come up with a skill that I gave to each model, and I put each of them in a sandbox, and I decided to tell them, hey, go ahead, look at this drawing set, take this skill, and to the best of your ability, identify what these different variables should be. Going through this process, I came up with something that was really, really interesting, and the AI models came up with things that I think were more interesting than what I could have possibly come up with. So really, there were different types of drawing sheets. Obviously, within the steel fabrication drawing set, there were 452 pages, and getting through that takes a trained eye. But as you'll see later on, these AI systems were able to pick up on the skills that I built out and gave to them based off of my own experience going through the workflow myself and really testing, kind of like training the models on what I was seeing and how they could better understand what these workflows looked like. You're going to have your framing and erection plans, your beam fabrication sheets, your column sheets, and then all these loose plates that were all part of these moment connections that we needed to identify, extract the proper information, and throw into the spreadsheet with. So skill development, how did I come up with the skill? Like I was saying before, I sat down and I probably went through 200 to 300 connections just on my own, reading the shop drawings, going through the spreadsheet, and doing this very, very manual. At first, it was taking me about like 10 minutes to do. As I got more comfortable with the shop drawings, it was taking me more about like 3 minutes to really get through one connection in a full go. And as I was doing this, I was tracking my logic. So for each cell, I would sit down and I would think about how I was finding the answer to that cell. And I pulled up a Word document. And for each cell, I would write out in the best English that I could every step and thought that I had to get to the answer that I thought was correct. And that was the basis of my skill. And then I started to go to different AI models. I was using the Opus 5, I was using GPT, and I would give it the skill and I would ask it, hey, find me this one specific cell that I knew the answer for previously, but I didn't check the answer to it was with the model. And I would see what it would get back. And whenever it would make a mistake, I would ask it, hey, why did you come to this conclusion? And I would try to teach it and train it and come up with a more detailed skill. And I use different models to do this. And I got this encompassing skill that at the end of it, I would give to each model independently and have it run to see if it can come up with the answers that were correct. This was a very iterative process, took a lot of time. I would say since I started this to when I'm making this video now that it's done, it took me about 2 weeks. Not working full like 60-hour weeks each time on this one thing. I would say I probably spent about 20 hours a week. So what, 40 hours in total to put together this skill, back test this information, and then put together this presentation that I'm going to show to you now. So for me, the biggest thing was how do I get the AI models to have a system of verification to eliminate the number of hallucinations that they would have and ultimately come to the right decision to populate the cell properly. Well, one thing that I did was just by identifying different members, different piece marks, different grids, different faces of the structural members, the elevations that these were occurring. So by taking all that information, I was able to kind of make like a global mind map for the AI of like where they should be looking for the information. And once they did that and they were able to start getting preliminary answers for what they thought was right, we needed to figure out different ways to verify whether the answers that they were coming up with were correct or were they just hallucinations or were they just wrong in general. So another thing that we were doing was cross-sourcing. So if it was able to find an answer on one sheet, we would ask the model to reference another sheet with identical information to verify whether the initial answer that it had come up with was correct or not. Another thing that we did was we were just checking different geometric properties within the drawing set, saying, okay, you have these different types of connections. Are you seeing that different connection in the same light on a different sheet? Number 4 was really interesting here, actually, the physical constraints. This is where the AI systems were coming up with verification methods that I would not have done as an engineer. And as I'm talking to more engineers in the space, they wouldn't have thought to do it that way either. We'll talk about that more in the presentation, but that was really interesting to me. And then the provenance of this was we really wanted to track how these AI systems were coming up with these answers. It's part of the experiment that I'm running here. So even if there was an incorrect answer, I wanted to know where that came from. Was it just looking in the wrong spot? Was it pulling the information in the drawing set from the incorrect source? Or was it just hallucinating and just making up a crazy, nonsensical answer? And through all of that, at the end of it, what we wanted to say was, hey, this answer is either sourced and it's verified, or is it not sourced? These are valuable things for me as the engineer trying to figure out what is truth here, to know at the end of the day, is there a high level of confidence from these AI systems in these answers or not? So this is the verification method, an example of it. And I didn't come up with this on my own, but I thought it was really interesting because there are different connection types with throughout this structural system. And typically what I would do when looking at, let's say, a flange plate was I'll find where the flange plate is located. I needed to figure out what the thickness of the flange plate was and what the effective width of the flange plate should be. And if you're trained in reading engineering drawings, that process really just looks like finding the piece mark, so going from the connection to the piece mark that you're trying to look for, and then looking at the different dimensions on that piece mark and then populating the cells with that. The AI system would do that, but when I was asking it different ways to verify these methods, one of the verification methods that it had suggested to me, and this was the Opus Claude model that suggested this to me, was when you're looking at steel shop drawings, and I'll pull it up here for those that are not as familiar. When you have steel shop drawings, there's what's called the bill of materials. And anyone in the construction industry, they're fully aware of what this is. But what this is, every member of steel is going to get a piece mark. So it's like its identification number. So this is like PL443. This is a web doubler plate here on the weak axis. And what you're going to look at here in the bill of materials is for each piece mark, they give you the dimensions. So the thickness, the length, the width. And then what you're going to notice as you're going through this, the bill of materials has like the rectangular geometry, but there are often times where the steel is cut into different notches, different shapes, like a T shape. And the bill of materials doesn't always reflect the shape of the T shape, but in the weight column, that's where the actual weight of the member. So if it's a T shape, the weight will be associated to the T, not the rectangle that it's shown in the bill of materials. And what the AI system decided to go ahead and use as a verification method was, let's go read the drawing of the piece mark, take out the geometric properties from the drawing that I am reading, multiply that volume by the density of steel, and then compare that overall weight that it got versus the bill of material. And this is something that I would not do. I have asked a lot of engineers if they do that when they're reviewing shop drawings, and I haven't heard anyone yet that does this same verification process, just because it's really tedious. Typically, when I'm reading through these drawings, if I have one verification point that I am confident in, that I could populate the cell in a way that I believe to be true, I will go ahead and I will do that. And I won't have 2, 3, 4 different layers of redundancy in these reviews, just because these things are time sensitive. And really, I want to be able to get this done as quickly as possible to keep construction moving. So once I feel very confident about one verification system, I'll move on that and I will make my decision and I'll be happy with that. These AI systems, they're not constrained the same way that I am necessarily. They could run while I'm sleeping. And one of these ways was to calculate the weight and use the weight as a different type of verification metric. I thought that was really interesting. Maybe if you don't work in the space, you don't think it is as interesting as I do. But everyone that I'm talking to that works in the structural engineering fields, they all thought that was pretty interesting. The fact that it was able to come up with its own verification method that I did not suggest for it to do, and now it's using it to get the correct answer and verify the answers that it's getting based off of this. To me, that was really, really interesting. So that was one of the verification methods that came up. It's probably the coolest one that it was able to figure out on its own. A lot of them were, for example, if you were trying to figure out what the column member was, it would look on plan. There's a call out on plan for the column size and the column piece mark, and then it would go into the elevation sections, and it would verify in the elevation and on plan that the two of those callouts were aligned, and that would be its verification system. So this is what the experimental setup looked like. Setting this up was interesting. Like I said, I think I said this before, I've tried to shoot this like 4 or 5 times now, and I keep stumbling over my own words, and I'm super embarrassed. So I've probably shot this now like 6 times, probably the 6th time that I'm doing it. But this is probably going to be the last time, hopefully, fingers crossed. The experimental setup was we had this drawing PDF, the 452-page shop drawing. I went ahead, I created a task skill and then a skill.me. And in the task skill, what that really was, hey, go follow the skill.md, the markdown, and follow every step verbatim, all the different data points that we want to track. And then at the end of it, take all of those data points and populate the spreadsheet that we are using as the final output. How did we get to an adjudicated version of the spreadsheet? Well, I did the initial takeoff, and I saved my initial takeoff. So I didn't check it. I just did the best job that I could possibly do, about 3 minutes per connection, and I saved it. And after that, what I would do is I would go back through each connection, and I went through each connection 3 to 4 times, depending on like the level of uncertainty that I had with the answers that I had given. And I just checked and checked and checked. And there were times that I had to change my initial answer. And that was the source that I used for the adjudicated version. What I did at the end of the experiment to make sure that the adjudicated version was truly correct was I took the AI results that I had gotten, and everywhere there was an inconsistency, I would look back at the condition to make sure that I didn't screw up 3 to 4 times and that the AI system was actually wrong. So that adjudicated model, what I did with that was it was the Excel spreadsheet. I downloaded it locally, and then I put it on a thumb drive. And I removed the thumb drive from my computer when I was running these AI systems, because what I was learning as I was going through this process, I was using the local computer models. So I was using like Claude Desktop, ChatGPT Desktop, and then the Grok build. I was not using the cloud-based AI systems, because what I was getting initially when I was doing this, I was using the cloud-based AI models. And what you get is this context like poisoning or leakage from previous conversations about the same project that you've had with different models. And I didn't want that to leak into the experiment that I was trying to run. I was trying my best to sandbox each model to truly see from a blank state how these models would take the initial directions and data that I was giving it and the output that we would get. So we would isolate and run these 4 different models. Like I said before, we were doing the Opus 5, the Fable 5, the Grok 4.6, GPT 5.6 Sol, and then my human baseline. So I did these all in isolation to the best of my ability. I really wanted to figure out what the truth was. So I ran each of these in isolation on my local computer. Each time I would get a run, I would export it to an air-gapped thumb drive so that it was no longer anywhere that I could find. I deleted it from my recycling bin. I really tried my best to make sure that there was no cheating that could occur, because I know that these models are really, really, really set on trying to find the right answer. And when you give it as many resources as you can, it will utilize every resource that you give it. And sometimes that means referencing a take from another model. So I really tried my best to make sure that didn't happen. And then once all 4 of those models plus my own were done, we would bring them into my local system. And then all I would do is check each model against the adjudicated version. And then that is the results that you're going to see here today. So again, like I was saying, we had these benchmarks. There was a freeze that occurred. So I ran these three. And then today on the 12th, I was like, I should probably try some different models, because I was curious to see how the other models performed. What you're going to see is that the original three were the best performing and the last two were not performing as well. But I was just generally curious about it. So as I'm working through this experiment, I initially scored and graded the first three on the left-hand side, which was the Opus 5 and the Fable 5 and the human. And when I saw those results, they were so good that I thought that I was doing something wrong. So I wanted to incorporate other AI models to see if I'm running the experiment wrong or if these models are just performing really well. And that's when I brought in the Grok model and the GPT model. And I was more comfortable with the results that I was getting from like a holistic experimental perspective. How was the scoring done? I decided to use a binary score. It's either the answer was right or it was wrong, and that's all that mattered to me. And that's what we were going to grade these systems based off of. I tried my best in the skill to come up with different methods when it comes to like heuristics. So if we were looking at the beam size, and when you're speccing out a wide flange, it's typically your one number, which is the depth, there's an X, and then there's another number, which is your linear weight of the member. If the X was lowercase or uppercase, that wouldn't trigger an incorrect answer. Again, with the bolt size, if one of the models decided to use a fraction instead of a decimal, those were things that were part of the skill that I wouldn't want to trigger an incorrect answer. Again, the most important thing here is figuring out what the truth is. So I was doing my best from the skill creation perspective to come up with all the different types of situations and scenarios that would maybe trigger a failure when it really wasn't a failure. So that's what the scoring method looks like. But at the end of the day, if it wasn't right, or if the system was unable to verify the answer, meaning maybe it found it in one place, but it couldn't verify it on another sheet or through a mathematical calculation or through some other verification method, then it would also be considered incorrect. So that was another facet to this. So the ground reveal is this. So there were 273 cells. The best performing model or participant in this experiment was the Fable 5. It got 265 cells correct. That's a 97.07 percentile of accuracy. The second place performer was the human. I got 264 cells correct. That's a 96.7% accuracy. Opus 5 was the third place. It got 263 out of 273 cells correct for a 96.35% score. Grok 4.6 got 246 out of the 273 cells correct for a 90.11 score. And the worst placing model was the GPT-5.6 Sol. It was able to get 159 out of 273 cells correct. So that's the overall final goal. But I think there's a lot more that goes into this and into these numbers that I'm going to jump into now. I don't want to just define the AI models by these blind metrics. I really want to give it its breadth and its day. Because one thing with this experiment, I don't want it to be seen as like a benchmark or like a judgment on these models in structural engineering as a whole. For me, what I was doing was I had this very specific workflow where I was working through a very tedious problem, and I felt like my time could have been used not going through all these shop drawings and extracting this data. I thought AI would be really good for it, and I found out that some of these systems are really good at it, but it does not by any means define like how good these models truly are. The data sample size was small, but I think that's kind of important because when people are working day to day, they don't have these data sizes typically that are just like infinite. They've got a very specific task with a very specific data point and workflow that they're trying to work within. And to be able to assess an AI model in that environment, I think it's like a real world application. I'm trying to make it as real world as I can because I'm doing this work contractually right now. Like these connections, they're getting redesigned right now, and there's a physical project that this is going to happen on, and I'm using AI to double check my work currently, and I wanted to see how good it was with this. So that's my 2 cents on that. So looking at each model, There were 21 total connections, and in each connection, like I was saying before, there are 13 different variables that need to be completed. So what this slide is showing is, of the 21 connections, how many full connections were modeled 100% accurate. And what you can see is Me the Human and Fable 5 scored the same at 14, were 100% correct. The Opus 5 was second best, where it scored 12 out of 21 connections correct. Grok 4.6 was 5 out of 21 connections correct. And the GPT-5.6 Sol didn't get any of the full connections correct. And this is another graphic. I think this was a very interesting graphic because it kind of showed me what the typical failure modes were within this model. So on the left-hand side, this is me, the human engineer, and you can really see my mistakes were kind of scattered all over the place. Like, there were 2 times where I got the beam size wrong. There was another time where I fat fingered the weak axis. And these are all mistakes, I think, as an engineer, that you make when you're either really decision fatigued, or you're distracted, or you're just not, you're human and you make a human mistake. And I'm making a lot of excuses for myself for not being better, but I really wanted to capture the reality of the situation. Like, I always try my best to be as good in the practice that I'm working on and what I am doing. But I'm human and I make mistakes, and you can see that here in this study right now. So my mistakes were very scattered. There was not like a specific variable that I couldn't figure out. It was me more just making dumb human mistakes. As you look at the other models, specifically the Claude models like the Opus 5 and the Fable 5, what you're going to see is, in the Opus 5, it had a really hard time with the bulk grade, which I was kind of surprised about. You could look here for 3 of the connections that are dotted but not fully colored in. Those are unverified, meaning that it was able to find the answer for the bolt grade in one location, but it couldn't find another location to verify what the grade of the bolt was. I thought that was interesting. And then also the top and bottom width. So when you're looking at the flange plate, the top and bottom plates, the width of that was very important for the calculation that we were running. We needed to define what that width was. And you can easily see that it was struggling with identifying that variable in the drawing set that we were giving it. You can see that for the beam sizes, the column sizes, the weak axis, and really all the shear connection data, it was perfect on. It was absolutely perfect. They made all of the right calls, made all the right decisions, and they extracted the right information, and it was perfect. As you look at the Grok 4.6, this trend only becomes more seen, where it really struggled trying to figure out what the flange widths were. And it pretty much got all of them wrong. What, it got 2, 4, 5 of them correct. So, I mean, it really struggled with the flange widths here. And for me, while I was training this skill, part of my training process was not only just verbally or like written talking to the model and telling it, hey, what is this answer? If it gets it wrong, tell me why you got it wrong. This is how you should be doing it to correct it in the future. I was taking screenshots. I was trying to highlight and annotate different drawings and share that with the models to really create a better skill. And as these AI models were running, it was not just like OCR that was running. It was itself like taking pictures, generating subagents, calling different tools. And I gave it a lot of freedom on how to get to the right answer from that perspective. I didn't put it in a box of like what agents or subagents or tools it could spin up to get the proper answer. I just wanted to see what it would do and how it would probably try its best to get to the correct answer. And then looking at the GPT-5.6, they struggled in multiple places. Trying to figure out exactly why it was struggling so heavily, but it didn't perform nearly as well as the other participants in the test. So I'm going to leave it at that for now. Again, kind of going back to accuracy by fields. When you're seeing like the longer stick and nodes here on the graph, that just means there's a lot of variance between models and the accuracy that these models could achieve. kind of talked about it before, but the smaller stick-in nodes, those were the variables that were probably the easiest to define, and the larger ones were the really difficult ones, like the flange plate thicknesses and the flange plate widths. And that's why I was talking before about the verification method of calculating the weight of the steel. I think the Claude models did that really well, and that's what really improved the accuracy for these two variables that were really hard. And I don't think the Grok model or the ChatGPT model could do that same verification process as accurately. And I think that was a giant differentiator here in the experiment that we ended up running. And again, this is the error distribution by field. So trying to figure out like which variables were the most error prone. The width of the top and bottom plates were the worst. That accounted for like 31.5% of all errors throughout the entire experiment. And then the second one to that was the thickness of that same plate. So really and I'm going to show you a specific example where the Opus model was able to figure out in the drawing set where the human actually made a mistake that was drafting the drawings. That's really interesting. We're going to show you that in a little bit. But when you look at the drawings, the fabricator was not a U.S. manufacturer or fabricator, excuse me. They were international. I'm based out of the United States, so they were international. And on the drawings, there were both empirical units and metric units, and that was confusing. And then they were just very like dense, and it's really hard for I think these visual models to get down to the pixel and parse through these really dense engineering drawings. And for a long time, I've always said that reading through engineering drawings is I call it like the most underrated form of intelligence. And that's why I really felt compelled to make this video, because when I saw how these models were operating, like even the Grok model that wasn't perfect, but a 90% is really good. Like if I got a student out of college, like his first day after they graduate, and I gave them this task, would they score a 90? I don't think all of them would, to be quite honest with you, especially like students that are studying like structural engineering. One of the things that I noticed when I was in school was you take a lot of courses on like differential equations or intro to structural analysis or all these different types of courses that are very much the mathematical portions of what it means to be an engineer, which I think are super important. But I don't think, and this is no shade to like how I was educated, a lot of it was definitely my fault. But I never felt like we had a class on like how to read engineering drawings or how to put them together properly. And it was something that I learned while working and practicing structural engineering. So the point being is that the fact that these AI models could perform really well doing that task of reading engineering drawings, I was really impressed by. And I think the majority of them performed way better than I thought that they probably could perform. So this is one of the situations, and I want to really talk about right now the biggest variable that gave us problems was this effective effective distance on the shear on the moment flanges. Excuse me. So let me go and pull up actually now is a specific plate, and I thought this was really interesting. So there is this flange on, I think it's 24. Yeah, it's 24. So to add some more context, the column is going in and out of page. This is like a bird's eye view if you're looking down at the column at this specific elevation. And the left-hand side is the left-hand beam going off at an angle. The right-hand side is an eastward beam going off at that angle. And then pointing down on the page is the south orientated beam. So the plate that we're looking at here is PL222. That is the piece mark identification number for this plate, and the number that we're looking for the effective width. So you see how it looks like a T here, this shape, it's like notched out. I'll zoom in more, it gets easier for you. So what we're trying to do is we're trying to figure out what the thinnest width is on that plate where the bolt group is occurring. And that is the width that we need. So we need this 159. That's what we're going to use in our calculations to see what the failure mode is at this section. And if you could look a little bit more to the right of that, there's this 319. And oftentimes what these AI models would do is what they would say, okay, they've identified the flange plate. They were able to get to this section. And from this section, they were able to identify that the flange plate piece mark number is PL222. What they would do from there is they would jump down to the piece mark bill of materials, and they would look here and they would say, oh, piece mark B PL222, the width is 319, and they would just run with that. They wouldn't go past that. They would take that as fact. They would go then to the section itself. They would say, oh, yeah, this is PL222. This is the dimension 319. Perfect. We have our verification system. We think it's 319. That's where we're going to go ahead and populate the cell with. That's what they did. What was interesting with the Claude models, and I want to emphasize this again because I didn't think to do it. Like when I was reading through these drawings, what I would do is I would go to the plan. I would figure out what the column piece mark number is. I would go to the search bar here in Bluebeam. I would enter the piece mark number. So in this case, it's C1307. It would take me to the first page of these drawings. I would go to the correct elevation. So we're at 32.1 elevation for this specific experiment that we're running. So that would take us here to section CC. I would go from section CC. I would come here to section CC, and then I would know intuitively, okay, we need the notched width here. I would see 159. I would take that. Okay, I read it right. Throw that into the Excel spreadsheet, and I would move on with my day. What Claude did to verify that 159 number was correct, it took all of these different geometric dimensions, figured out what the volume of steel for the plate should be, multiplied it by the density of steel, and then came down to the piece mark number, the bill of materials, found the piece mark number, and then equated that mass with the mass that it had calculated. I don't know if AGI is a thing or if it's real, but people always say there are moments where you can kind of feel the AGI. And when it started doing this on its own, unprompted, that was one of those situations where it felt like the system was not just like reading off a script, like it was really reasoning and deducing a very complex problem and a solution to that problem. So again, I want to emphasize again that I was really impressed by how it was able to do that. So this is that same example. And so the correct answer is 159. This was each model and their answers to that problem. So Grok went to the bill of materials. It came back with a 319. That was wrong. The human me, I was able to read it and say that it was right. Opus, I don't know if Opus was able to probably run the calculation correctly. So it didn't get the correct verification number twice. So it answered this question as unverified. Table 5 was smart enough to do it. It found two different data points. It read it on plan. It calculated the density of steel and then figured out that the width that it was estimating was correct. It gave us the correct answer here. And then GPT-5.6, I'm still trying to kind of go through all this data and figure out how it came up with that answer. Whether it was like a hallucination or not, or it got it from somewhere else, I don't know. From what I could tell in the data that I've looked at, it wasn't really hallucinating. It was just looking at the wrong objects and extracting data points from the wrong objects. And then once that upstream data point was wrong, it found downstream other ways to verify that incorrect information, and it thought that it was correct when it wasn't. So even when you have these verification systems that are built out, if an initial assumption or decision made by the model is wrong, even if you have those downstream verification systems, it can still convince itself it's right when it's really not. That's what I'm learning here in real time. So again, this is the 5.6 Sol results. As you can see, it got none of the flange plate information right. The moment bolts, it had a really hard time identifying. Bolt rate did a great job on. Give it credit where credit's due. Bolt diameter and the shear connection, it was really good on. I will say some of the easier problems, like the beam size and the column size, it got two of those wrong, which I was kind of surprised about, but it did get those wrong. The weak axis connection, it got a majority of them wrong as well, which I was very surprised about, because for this specific project, depending on whether the connection was east, west, north, or south, determined the weak or strong axis, because every wide flange column was orientated in the same direction. So when a connection was spanning north or south, it was always on the flanges of the wide flange columns, meaning that it was a strong axis connection, as opposed to if the connection was west or east, those were always going to be weak axis connections. And that logic was built into the skill that was very project specific here. But even with that information, the GPT model wasn't able to get it right every time. So that was a little disappointing, I would say. But overall, almost 60% for an artificial intelligence system, I mean, is what it is. What I was very interested in was the unverified cells. I thought that it would be able to even if it didn't know the answer, it wouldn't convince itself that the answer that it got was correct. And the lack of unverified cells says to me was it was able to convince itself that it had the right answer when it didn't. And that's dangerous. Like from my perspective as a structural engineer, it would be much more valuable for me to get an answer from an AI model saying, hey, this answer is unverified. You as the user go back. And every answer that I do give you is verified to the verification steps that we've agreed upon. That would be better to me than just telling me something's right when it's not. So that was a little upsetting as well. It didn't spin up any sub agents, which I have to go back and double check. In my skills, I'm always asking it to track all the subagents that it's using. So I do take it as fact. If it says that it didn't turn any up, then I believe that. But I was a little upset about that as well. This is the Grok answers. Again, no unverified cells. Like for the flange widths, I would have liked it better if it just told me that it didn't know the answer as opposed to acting like it knew the answer. It did flag a bunch of the registered answers though. So what a flag would be here was, hey, I've got a low confidence on whether this is correct. This is different than the unverified because what the unverified says is, I came up with this one answer. I think it's right, but I don't have other places in the drawings to confirm that it's correct. What the flag register tells you is, hey, I came up with this answer. I could find other ways to verify it, but I don't know if this global picture that I'm looking at in this instance is actually correct. So that's what the flag instances were. And then it did spin up 3 sub agents. So when I look at the sub agents as well, it's like, where are those sub agents doing? What kind of Python scripts are they writing? All of that's been saved locally, and I'll inspect them more later to kind of identify what different sub agents they decided to spin up. But again, we're going on like 42 minutes here. There's so much information to go through, and I'm piecing through it in real time here. So this is just kind of how I ran the experiment and all the data points I wanted to track. Part of this experiment was not only getting a AI model to just do this task and see how accurately it could do it. I'm really curious when you give an AI model a task and you give it certain constraints, you give it certain data points, like what does it do in order to get the correct answer? And like when I was running it on the cloud, I saw that it was going to previous chats that I had, or even when I was running it locally and I still had the adjudicated file on my local, it would go and it would reference that. So it's trying to find the correct answer. And what I've noticed is whatever options you give it, it will go and it'll utilize every option. And I think what we are trying to struggle with right now is we don't understand all the options that we're giving these things. We don't understand that it could build a Python code and break out of your sandbox. And that's why air gapping for me was the best way to really try to isolate these models. The best way that I could was just physically making sure that there was no way that it can get to it. But I think that's really interesting is like trying to almost reverse engineer, not like from like a model weights perspective, but just from like a logic and reasoning perspective of how these models are going through really complex tasks and what agents they need to build up and how they're going to actually get to these answers. I think all of that is really, really interesting. And I'm trying to figure that out as I'm going through this experiment. And then these were the Opus and the Fable 5 models. I think Opus did a really good job at figuring out which cells were unverified. What did it get? It got 263 out of 273. And for me, like I was saying before, it was very binary. So I was treating the unverified as incorrect. But if I was working as an engineer and I trained or I built this skill and I had Opus go do this, I don't know if I would necessarily judge the unverified cells as incorrect, because what that's telling me as an engineer is there are these 5 cells in Opus's case here for this experiment that it couldn't figure out. So I know as the engineer, I need to go jump in and I need to figure those out. And that saves me a lot of time. If it could figure everything else out and then just tell me where it doesn't know and everything else is correct, very valuable to me. So let's say if I was going to treat those as facts, that gets us to 268 divided by 273. That brings you to a 98% accuracy for the Opus 5 model. I thought that was really interesting, really, really interesting. And I think it did the best job of identifying the unverified cells as possible. Again, it registered 9 flag entries, and then it spun up 7 subagents. The Claude Fable 5, this was just gas, and I mean that in every positive sense of the word that I could possibly use. I think it's just really powerful, that model. It really didn't spin up any subagents. It didn't like say any of the cells were unverified. It only flagged 6 of them, but it still scored the best out of everybody in the experiment, myself included. Um, yeah, I think the Fable 5 model is just really a lot of horsepower. There's a lot of horsepower in that model from what I can see. Not even just this experiment, but just using it over the past couple of days. It just is a lot of horsepower in that model. And the execution strategies, I was trying to track, again, the subagents that were created, the tool calls that were used, the shell commands that were used, the PNGs written to disk. So this was these models would go ahead and they would take screenshots as they were working, and they would use a VLM of some sort, I would assume, on the back end to understand what they were looking at to come to the right answer. And then these were images actually viewed by the model. Some of these data points weren't available, unfortunately, for the Anthropic models. So this is kind of like a null and void point here at the bottom. But again, I really want to understand how these models are operating, what they are doing, to come up with the answers that we are witnessing on the experimental side. So I thought this was really interesting. Who's taking more pictures, who's spinning up more subagents. It seems like the Opus 5 model loved the tool calling, and the Grok 4.6 loved taking pictures and then writing them to disk. So I thought that was really interesting. And I will say the common denominator here was the more of these strategies that the model used, the better that it performed outside of the Fable 5, which performed the best. So that's why I was saying before, I think the Fable 5 is just a lot of horsepower behind it. I think it's just a really good model. But the other 2 models, the Opus 5 and the Grok 4.6, they might not be as capable from a model perspective as Fable 5, but they're capable in the sense where they could build out a lot of interesting tooling to make their capabilities greater, if that makes sense. So that's just what I'm seeing here. And then runtime. So this was interesting. This plays into the practicality portions of this as well, because as an engineer, like I was saying, there were 21 connections that we were looking to design for this specific experiment. By the time I'd gotten to this portion of the structure, I already knew the shop drawings pretty well, and I timed myself at about 3 minutes per connection. So that's 63 minutes, about an hour and 3 minutes that it took me to get through this experiment. And what I wanted to do was time myself and then see how long it would take the AI models to do it. Not because, I get it, you can get an AI model to do something, let it run in the background, and you can do your other work. I was just generally curious what the comparison was. The Claude Opus 5 ran in an hour 40, Fable 5 ran in an hour 30, Grok 4.6 ran in 39 minutes, and then GPT 5.6 Sol ran in 46 minutes. So what I noticed when I was running these is the time themselves wasn't really an indicator of who performed better, or it really wasn't like a hamstring to me. It's not like one ran in 10 hours and then one ran in 45 minutes. They were relatively all in the same ballpark, where from a production standpoint as an engineer, I could live with waiting 40 extra minutes or 30 extra minutes for an output if it meant the output was going to be better. The one part that I thought was interesting was the interruptions. And as I move towards my conclusion at the end of this plays a big part of it. The Fable 5 had an interruption midway through. There was one, and this was not because I closed my laptop or my computer died or anything like that. I ran into a token wall, and the Fable 5 has a lot of horsepower. I get that, but it's also throttles. And if I were to use it in production, I realized that in the hour that I was using it originally, it took up all of the credits that Anthropic allows me to use with them. And I wouldn't want to rely on a model that would just time out that easily, and then I have to wait 5 hours and 60 minutes before I can interact with that model and then run again. So that interruption was very interesting to me. The GPT-5, the 4.6 or 5.6, excuse me, One of those interruptions was my fault. So I had to leave for a meeting and I left my computer running, and then my computer died because I forgot to plug it in. And I will say I don't think, and I know that it's not a reflection on the results. And the reason why I say that is because I ran it again a second time and it actually scored worse. So I'm giving its performance a better grade here this time. And then the second time it did time out from credit usage. Um, for me, it's like I was saying before, best way that I could articulate it right now at 9:30 at night after working for 14, 15 hours is, as an engineer, I'm comfortable with giving these agents like 2 hours, 3 hours to work on a task, a highly complex task, if the answer they give me is really accurate. When it starts to come from oh, I've used up all of my credits and now I can't use it until 5 or 6 hours later, that's a little bit of a hamstring. And also from am I using like free programs or not? I'm paying for all of these. So I pay for Anthropic, the Max program, the GPT Pro program, which is like the $100 a month. So $100 a month, $100 a month, and then the Grok one, I pay the $30 a month one for as well. So these aren't the free programs either. Like I am paying for these AI systems. I want as little downtime as possible. So if I could find a model that's has a longer like run time and I can use it more often for the same amount of money, I would rather use a model like that as opposed to like the Fable 5, which is super powerful, but I can't really use it as much, so it's less valuable to me. I hope that makes sense. Tokens and cash usage. So I also wanted to track the number of tokens that were being used throughout this. Unfortunately, through Grok Build, I haven't been able to figure out how to get the token usage. I'm not sure if they give that to us. I know that there's a lot going on over there at Space X AI. And if anyone from there has made it 52 minutes into this video and would love to show me how I could track the token usage, I would love to learn about that. I'm not AI native. I'm a structural engineer with super intelligence, trying to figure all this out to the best of my ability. So I'm really trying my best. And if there are errors throughout this experiment, please let me know. I won't take it personal. I really want to just like figure out the best way to do these things. So if anyone knows how to figure out what the token usage for the Grok models through Grok builds, that would be great for me to know, and I would really appreciate that. But what I noticed from a token usage perspective, the Claude models were really token efficient. Like, I don't know what happened with the GPT 5.6 model, but I don't know why the input tokens were 15.7 million, 15.8 million. Everybody got the same amount of data. Everyone got the same skills, verbatim, same skills, same drawing set, and same input spreadsheet to look at. And then also they all got the same kickoff message as well. I tried to keep it as variable constant as possible on that ends. And the only thing that I could see that was different from model to model was the actual model that we were using for the experiment. So I don't really know what happened there from like a token input perspective. But it seems like looking at the Opus models, if you're looking at the cash tokens, like Opus used a bunch of cash tokens, and it got really close to its cash hit rate of almost 100. And then same thing with the Fable 5 model, like it was really running up the cash tokens as well, where the GPT model was much more efficient from like a cached tokens perspective. And to be honest, I'm not going to act like I know what like the significance of a cached token in a large language model really means or is. I just know that there are limits to those when I'm using the models. So for me, I don't want to run into those limit walls. Again, another place where I'm trying to learn more on like the significance of like what those cached tokens are. It's part of this whole experiment. So I hope that you give me some grace there. What is execution metrics? Kind of similar to what we've been looking at before. The first row I think here is interesting. We've kind of talked about the last rows, but the first row I think is interesting, and this is where the source trace comes from. So for every answer, there has to be a specific place within the drawing set where it got that answer from. And what I was trying to do here with this verification method was eliminate hallucinations. So for Opus and for Fable, they both were able to find a source within the drawing set where it got an answer from, regardless if it was correct or incorrect. It was able to source each answer, meaning that it didn't hallucinate any answers. Grok 4.6 was also really, really good at this. It got a 269 out of 273, which I thought was really interesting. It was very, very good about not hallucinating for the majority of the time. There were only 4 hallucinations there. And GPT 5.6 was just not as good, unfortunately. And I think that was reflected in the accuracy that it ended up showing toward the end, because it did hallucinate a lot. And then the last slide. So what was this experiment? Like, what was the point of it? The point really for me was, hey, I'm really fascinated with structural engineering. I'm really fascinated with AI. I'm working right now as a structural engineer and practicing it. And I had this workflow I thought AI would be really good for. Originally, I was just trying to get AI to do it for me. And as I was going down that road, I realized that it would be more useful for myself to really turn it into like an experiment. Like, I think a lot of times in AI, people are trying to build startups and products, and like I'm trying to do that myself. Um, but I think sometimes I would lose sight of, hey, it would be really useful if instead of just trying to build a product, like run an experiment and like just see what these models are doing and really understand them at the best base level that you could identify. That's what I'm trying to do here in this experiment. I finished up running the last 5.6 run this afternoon. So I haven't had a lot of time to let this information like really marinate. I was just super excited about what I saw, and I wanted to make a video about it while I had the energy to do it, because it's really not easy for me to like sit in front of a camera and like talk for an hour about everything that I'm working on. So I wanted to take advantage of that now. But that was really the point, was like, hey, in a real world application, how effective are these models? And how are they being used? What are the best ways to use them? How do I formulate skills? I think all of these conversations that I was having with myself while going through this, I found them interesting, and I hope that you do as well. What I look to do in the future is take more examples like this, like different workflows that I'm working on. So, for example, I have to start doing a lot of drafting in Revit. So I'm going to start trying to build out the MCP between Revit and all these different AI models and sample a workflow like I'm doing now, and try to figure out which types of models and which types of workflows pair really well. And I'm going to try to do that for as many workflows as I can identify. And I'm going to try to do it as similar to what I've done now, like sandbox them, isolate them, and try to understand like at their core which ones are operating the best way that they can. And as I learn more doing these experiments, they'll definitely get cleaner than what I'm doing now. Like I don't, again, like I don't want this to be seen as like a benchmarking by any means. It's not. It's just me and my day-to-day role using these different models, which one was the most effective and provided me the most value. And how did I go about orchestrating an environment to do it? That's really what this experience that you're witnessing right now is. And I was really fired up about it. I think it did really, really well. Like the Grok model performed way better than I thought it would. Like I know there's a lot of turnover from the third party external perspective of me viewing it on X. Like I know there's a lot of shakeup and turnover there, but with Grokbot and now with Grok builds, I was actually really impressed with the model quality, and that it outperformed OpenAI's model. I will say I was a little disappointed in OpenAI's model. I thought that it would have performed better on this task. They really are like I'm disappointed in it because I use OpenAI's interface and models more than any other model, to be honest. When it comes to engineering work, I think I use Anthropic's models the most. But on a day-to-day basis of like asking and talking to AI, I've been speaking to OpenAI's models since what, like 23. So it's been 3 going on 4 years now. And I really thought that it would have performed better in this task. And that's not a crucifixion of like how good the team is over there or like what the model itself is able to perform. Like I keep saying, this is not a benchmark. This is a very small sample size, but it is really what I'm working on. And like this is what I would want it to do as someone practicing structural engineering. So I wanted that to be shown here in this video, and I look forward to doing more things like this in the future. So thank you very much. I really appreciate it. If you're still here listening to me ramble about this, I'm really trying my best to build real time in real workflows in the construction industry, in specifically the structural engineering industry, where I've done most of my professional career in. And I'm trying to figure out, hey, how could we use these AI systems to make me a better engineer, to help build things better in the real world, um, and really just trying to see like what the capabilities are and how this can make us better at what we're doing. So I'm gonna keep doing that. If you have any suggestions for like workflows you'd like to see me test or work on, feel free to shoot me like a DM or put it in the comments or like wherever this could be. I'm all ears. I would love to work on workflows that you're interested in as well. If there's something that you would like for me to do or work on, just let me know, and I'll try my best to do it. So we're right right at an hour right now, and it's 9:36, which is a good time in my mind. So thank you very much. I'm going to close it out at this. And thank you very much. God bless. Peace be with you. I appreciate your time.